After studying this chapter, you should be able to do the following. Describe the mechanism of crack propagation for both ductile and brittle fractures. Explain why the strength of brittle materials are much lower than predicted by theoretical calculations. Define fracture toughness in terms of a brief statement and an equation. And also be able to define all the parameters in this equation, including the proper units. Make a distinction between fracture toughness and plane strain fracture toughness. Name and describe the two impact fracture testing techniques. Define fatigue and specify the conditions under which it occurs. From a fatigue plot for some material, determine the fatigue lifetime and the fatigue strength at a specified number of cycles. Define creep and specify the conditions under which it occurs. Given a creep plot for some material, determine the steady-state creep rate and the rupture lifetime. Let's first take a look at some engineering failure examples to see why it is important to learn failure mechanism. So this is an oil tanker that fractured in a brittle manner as a result of the propagation of a crack completely around its girth. So brittle fracture usually happens without warning. So it just happened quickly. So there's no time to prevent the fracture from happening in this case. Another example is a Boeing 737 commercial aircraft, which experienced an explosive decompression and structural failure on April 28, 1988. And an investigation of the accident concluded that the cause was fatigue. So we're going to learn fatigue and brittle fracture later in the lectures. But you can see that both failures are catastrophic. So the failure of engineering materials is almost always an undesirable event for several reasons. This includes putting human lives in jeopardy, causing economic losses, and interfering with the availability of products and services. Thus, it is important to understand the mechanics of the various failure modes. So in these lectures, we're going to talk about the three failure modes, including fracture, fatigue, and creep. And it is important to be familiar with appropriate design principles that may be employed to prevent in-service failures. So we said that the failure of engineering materials is almost always, we didn't say it's always an undesirable event, because the common causes of failure include improper material selection and processing, inadequate design of the component, and its misuse. And the three failure modes that we're going to discuss in the following lectures include fracture, fatigue, and creep. Simple fracture is the separation of a body into two or more pieces in response to an imposed stress that is static, which means it's constant or slowly changing with time, and at temperatures that are low relative to the melting temperature of the material. For metals, there are two fracture modes, ductile fracture and brittle fracture. The classification is based on the ability of the material to experience plastic deformation before the final fracture stage. Any fracture process involves two steps: the crack formation and crack propagation in response to an imposed stress. And we mentioned that there are two fracture modes, ductile and brittle modes. So ductile and brittle are actually relative terms. Whether a particular fracture is one mode or the other depends on the situation. Ductility may be quantified in terms of percent elongation and percent reduction in area. Furthermore, ductility is a function of temperature and the strain rate and the stress rate when a certain stress is applied. So therefore, we cannot simply say if the material is ductile, then the fracture is ductile, or if the material is brittle, the fracture is brittle. Instead, the mode of fracture is highly dependent on the mechanism of crack propagation. So for ductile fracture, the crack propagation is slow and it requires an increase in applied stress. Such a crack is often cited to be stable. That is, it resists any further extension unless there is an increase in the applied stress. On the other hand, the brittle fracture crack propagation is fast and continues spontaneously without an increase in applied stress. In conclusion, for ductile fracture, it has slow crack propagation, and which is accompanied by significant plastic deformation. It fails with warning. For brittle fracture, the crack propagation is rapid. It has little or no plastic deformation and fails without warning. So the ductile fracture is almost always preferred over the brittle fracture for two reasons. First, the brittle fracture occurs suddenly and catastrophically without any warning. This is a consequence of the spontaneous and rapid crack propagation. On the other hand, for ductile fracture, the presence of the plastic deformation gives warning that fracture is going to happen, which allows preventive measures to be taken. Second, more strain energy is required, or more energy generally is required to induce ductile fracture. So these materials are usually or generally tougher. Ductile fracture surfaces have distinctive features on both macroscopic and microscopic levels. The figures down here shows schematic representations for two characteristic macroscopic fracture profiles, and also there's one brittle fracture profile. The first configuration is found for extremely soft metals such as pure gold and lead at room temperature, and other metals, polymers, and inorganic glasses at elevated temperatures. These highly ductile materials neck down to a point fracture, showing virtually 100% reduction in area. The most common type of tensile fracture profile for ductile materials is the second, where fracture is preceded by only a moderate amount of necking. And again, in comparison, here is the fracture profile for brittle fracture. It has very small plastic deformation in terms of percentage area reduction and percent elongation. So again, the ductile fracture is usually more desirable than brittle fracture because it has warning before fracture, whereas for brittle fracture there is no warning. Sometimes we can tell which type of fracture by observing the fracture surface. So for plastic fracture, it has this characteristic surface contour, which is termed as cup and cone fracture, because one of the matching surfaces is in the form of a cup and the other like a cone. So this is indicative of plastic deformation. Whereas for brittle fracture, the fracture surface is very bright and shiny and smooth with no or little plastic deformation. Here's another example for the pipe fracture, in which gives us very clear comparison between the ductile fracture and the brittle fracture. Let's say that pipe might be the same type of pipe, and ductile fracture might happen in summer due to some excessive forces, and the fracture results in a large deformation. It's just cracked open, but the pipe is still one piece. On the bottom, which is the brittle fracture, the pipe breaks into many pieces. This might happen in the winter where the temperature is very low, and the pipe, if it's polymer, made from polymer, it becomes very brittle and it breaks into pieces, but each piece have a very small deformation. Now we can compare the ductile and brittle fractures from microscopic perspective. First, the deformation. Ductile fracture has extensive plastic deformation, whereas brittle fracture has little or none. And for ductile, the crack propagation is slow and it needs increased stress for the crack to grow. For brittle, the crack propagation is fast. It continues spontaneously without increasing stress. And type of materials, most metals will have ductile fracture at a temperature that is not too cold. For brittle, it usually happens in ceramics or cold metals. And ductile fracture has some warning because of the permanent elongation or extensive plastic deformation. It gives warning. But for brittle fracture, there is no warning before the fracture happens. For the strain energy, because of the plastic deformation, again, the ductile fracture requires a large amount of strain energy, whereas for brittle, the strain energy is lower. The fracture surface for ductile fracture is rough. It has the characteristic cup and cone fracture surface, but for brittle fracture, it's smoother with no or very little plastic deformation. Ductile fracture experiences the necking phenomena. For brittle fracture, there is no neck formed at the fracture surface. So how did the ductile fracture happen? Or what is the fracture process during the ductile fracture? We're going to use moderate ductile fracture as an example to explain the fracture stages for the ductile fracture process. For a specimen under tensile test, first after necking, small cavities or micro voids start to form in the interior of the cross section. Next, as the deformation continues, these micro voids enlarge, come together, and coalesce to form a larger crack, which has its long axis perpendicular to the stress direction. So this is the stress direction along the axial direction, and this is the long axis of the crack, so they are perpendicular to each other. The crack continues to grow in the direction parallel to its major axis by the microvoids coalescence process, because more microvoids start to join in this direction. And finally, fracture happens by the rapid propagation of a crack around its outer perimeter of the neck by a shear deformation at an angle of 45 degrees with the tensile axis. Because this angle is where the maximum shear stress happens. And here is the cup and cone feature from the ductile fracture. And again, this angle is about 45 degrees with the tensile stress. And also, microvoids usually happens around the particles, which is from during the solidification process when we make the materials. Some inclusives may be left in, or some impurities are left in the material. So those particles will be served as void nucleation sites. And voids start to form around those particle sites and grow to a bigger crack and finally become the fracture. At microscopic level, ductile fracture normally occur in transgranular fashion and creates dimples on the fracture surface. So transgranular fashion means the fracture cracks pass through the grains. So it's not along the grain boundaries, but it actually goes through different grains. So this is the transgranular fashion, or transgranular crack growth. And dimples are formed on the crack surface. There are two types of dimples. One is equiaxis dimples, which are formed at the places where the micro cracks are formed. And another type is called the elongated dimples, and they are formed on the shear lip because of the plastic deformation, and they point towards the origin of the failure. And by the way, the dimples are better studied using the MERSEM, which is scanning electron microscopy, which has better resolution and depth of field than does the optical microscope. Brittle fracture takes place without little to no plastic deformation and by rapid crack propagation. The direction of crack motion is very nearly perpendicular to the direction of the applied tensile stress and yields a relatively flat fracture surface. Fracture surfaces of materials that fail in a brittle manner have distinctive patterns. For example, they don't have any or very little plastic deformations. In addition, in some steel pieces, a series of V-shaped showering markings may form near the center of the fracture cross-section that point back to the crack initiation site. So there are two examples. You can see those V-shaped cracks, and all of them pointing back to the point or to the site where the initial crack generated or originated. So if you see this showering pattern, that must be a brittle fracture. From microscopic level, the brittle fracture has two modes. The first type is transgranular fracture or cleavage. So for transgranular fracture, the crack propagation, this is the crack path of the crack propagation, corresponds to breaking of atomic bonds along specific crystallographic planes. And this fracture, or the cracks, pass through the grains. It doesn't go around the grain boundaries, but it passes through the grains. For some other materials, the brittle fracture happens intergranularly. That means the crack propagation is along the grain boundaries. And this is termed as intergranular fracture.